Welcome, fellas. I'm Tobias Ivarsson. This handsome man over here is Anders Taylor. We're gonna not only do an awesome presentation on how graph databases can make you guys superstars at your job, but we're also gonna prove to everyone that in Denmark, the theory of never have a meeting right before lunch isn't true. So let's start by setting the stage. We are all developers. Everyone in this room, I assume we're all developers. We're developers, and you guys work with software for a living. As developers, we want to get stuff done. We want to make awesome software that solves the problem, that solves it well in an efficient manner. We want maintainable software that we can evolve over time. We want reliable software, as few bugs as possible, as predictable timing behavior as possible. All of this is what we expect from what's expected from us, and that we thus expect from the libraries and products that we use. So from a database, we want fast responses. We want our database to be fast at the kind of queries we're doing against the database. We also want, and this is even more important, to trust the database with our data. Once we put data in our database, it should stay there until we say otherwise. It should be consistent in the way that it's stored. It should not change unless we tell it to change. It should be internally consistent. It should not be should not be violating any of the constraints that we have on the database. I've written notes here. They're unimportant. So how do we do? What databases do we use for all of this in the modern world? A long time ago, in what feels like it was a galaxy far away, there were many different kinds of databases. There were network-oriented databases, relational databases, and document-oriented databases. These were just a few among many. Then, for some reason, the relational empire grew strong until all of the land was under its rule. Lately, a group of young rebels have grown in strength and are challenging the mighty Death Star that is the relational empire. Neo4j is one of those databases. And in the beginning of the third millennia of the current calendar, a small company in Sweden rose as one of these rebels. Their data model was a graph, and their name was Neo4j. In 2011, they gathered a group of fellow developers in Copenhagen to tell them, to share their ideas on how these graph databases can make all of us superstars. And that is what we're here to do today. We work at this company called Neo Technology that developed this graph database. So as I said, the relational database has been the dominant model for years and years now. It really feels like it was another world before the relational model was the dominant one. And we've all, as developers working with relational databases, we've probably all dealt with the pains that can come with the relational model. I'm talking about things such as trying to fit your domain model into the into the table form, the physical model of a relational database, where you start with a nice entity diagram and you shuffle it around to create tables and artificial tables such as joint tables, and maybe you have attributes that don't really fit. You have them only in a few. You have maybe a different set of attributes for different entities. So you create a attribute table And all of these kind of weird artificial constructs in order to fit your model into the relational database. This leads to headaches at best, but more likely it leads to a harder to maintain database schema and harder to maintain software. And in the worst case, you get performance degradation from the joins you have to do to get to your core data. I'm sure that everyone has been in this kind of situation. I know my first project as a software developer 10 years ago, I was building a web shop for a customer of mine. And this web shop had products, since that was what we were selling. It was musical instruments. They were divided into categories, and my customer wanted to be able to add new categories and move the products from between the categories and restructure and add products dynamically. I don't think he ever did, but he wanted that. And so I created this schema of a category table and a product table, and all of the products had name and price, but they could also have other attributes. So I had an attributes table where I listed how the key value pairs for each entity in the products table. And I noticed that, sure, it worked well, but there was a noticeable speed difference between just 100 and 200 products in this system. So what are the alternatives to the relational model? What are these rebels that we talk about? Well, there are key value stores that are just simply storing a simple value. It can be anything associated with a key. There are document databases that have more structure, that are kind of like the key value stores, but the values they store are more structured. They're documents, so the database can reason a bit about these stored entities. Then we have column family databases, such as Google Bigtable. They are kind of like relational in that, they expose some sort of table model, but you can have, in some of them, you can have multiple values for a column for the same row, and they are structured differently internally than a classical relational database. And then, of course, we have graph databases, which is what we're focusing on here today. The key point of this is not that you should all go out and use a relational database for everything that you're going to do from here on out. What we want you to take away from here is that you should use, for each problem that you're trying to solve, you should look at, okay, what is my data model? How do I best represent this? And choose a storage model that's suited for that particular domain. This might not be just one. It might be that you have to combine two or more data stores. But we want you to, when you're solving a problem, look at what is the problem I'm trying to solve, how should I structure my data, and how should I store it to be able to do my queries as efficiently as possible. And that's really the key thing. You want your normal execution of your application to be as smooth as possible. And these different databases that I mentioned focus on slightly different things. The focus of the key value stores is mainly on scaling to large volumes of data, huge volumes. They do this by having this very simple notion that they do, that values are completely opaque to the database, which means that all the database knows about is the key and that there's some thing associated with it. This means that you can partition data across many different instances, so many different machines, which is something that's hard to do in a relational database because data is, if you split a table across multiple instances, multiple nodes in a network, you cannot do joins over that table. But since the key value stores do away with joins, they say, okay, this is for efficiently storing something where you don't need that. They can partition their data in a very efficient manner. Column family databases and document databases move slightly more towards the complexity scale on this axis. They try to model more, slightly more complex data. The database knows more about the data than in a key value store, but they're still focusing on trying to scale to larger volumes and achieving higher throughput than what you can get with a relational database. Graph databases take a slightly different approach. We focus on solving the complexity in your data. So we focus on the connections between your data entities and supporting deep queries, and I'll show you how we solve more complicated domain models as well. But I mean, still, this is billions of nodes and billions of relationships. And size-wise, most of all use cases are well below in size of what any of these databases can handle. So as I said, for each task that you're working on, you should learn the different tools at hand and use the appropriate one for each task. And we're telling you about graph databases. And in particular, we're using Neo4j as an example because Neo4j is a graph database, and Neo4j is the graph database that we know and work on. Okay, I've talked about different databases, and I've talked about graph databases, and that Neo4j is a graph database. But what is a graph database? A graph database is a database that stores your data as nodes. So you have nodes in your database. These nodes represent entities. So here we have a very tiny graph with one node that represents James, one node that represents Mary, and one that represents a Volvo. So these are different entities of different types. We have two persons and one car, but they're all represented as nodes. Then we have relationships between these nodes. And relationships in a graph database have types, and the types denote how these entities are interrelated. So in this case, James lives with Mary, and James loves Mary. We see that from the type and the direction. All relationships have a direction, but it's up to your application to determine what the semantics of that direction is. In this case, I would say that the lives with relationship, for that one, I don't care about the direction. If James lives with Mary, Mary obviously lives with James as well. But for the loves relationship, it's not necessarily so that that the direction doesn't matter. Just because James loves Mary doesn't mean that Mary loves James, but in fact she does. And thus I add a relationship from Mary to James that says that she loves him as well. Finally, we have properties on these entities. And properties are just key value pairs associated with the nodes. And we also have properties associated with the relationships. So in this case, we can get information about these entities from the node. So we can get the name of the James node and see that, yes, his name is James and Mary's name is Mary. And they're aged 32 and 35. They own a car. It's a Volvo. It's a V70. James bought it last year, roughly a year ago. Okay, so that's the data model. Nodes, relationships, and properties. Pretty simple. how do you query it? Graphs are queried by something called traversals. And a traversal is really just a walk through the graph. You start at some starting point, and then it walks through the graph, finding the information that you're looking for. As an example of a traversal, it's a classical social network example, friends of a friend. Given a person, what are the friends of his friends that he doesn't already know? Friends of his friends, or her friends. To find this, we traverse each of the starting node's friends, and for each of those friends, we traverse all of their friends, ending up with this set of green nodes that we see here. So the green nodes the yellow nodes are the friends of the me node, and the green nodes are the friends of their friends. So my friend of a friend's. And that is our result set. Okay, so you traverse the graph to get the information. How does the result look like? What does it look like? Looks like this. You get a path returned for each of the friend of a friend, each FOF that you find. It returns the path from the start node to that FOF. So I get one path that looks like this, another path that looks like this. In this case, they go through the same friend node, but end up in different FOF nodes, and so on and so forth for all of these green nodes. Second question. Okay, so we know how to, given a start node, find information in its network. How do we find the start node? We use an index. Indexes in Neo4j are simple lookup indexes. You use them to look up one or several starting points from which you then traverse to get the full information that you're looking for. So in this case, to find the me node, I would look up in an index based on my username. Thobe is the name I usually use online. So that would find the me node. Andres, if I looked up using Andres, I would find the him node. And I could also look up other persons in this index. Okay, so that's the graph database model. We have nodes, relationships, and properties, traversals to query it, indexes to find starting points to start a traversal at. So how about this Neo4j graph database? What does it do? Neo4j is a fully transactional graph database. While many other NoSQL databases do away with transaction support and full ACID transactions, Neo4j embraced that stuff. So Neo4j is fully ACID transactional, and quick reminder of ACID, the A is for atomicity. So, which means that when a transaction in Neo4j commits, when you have a transaction in Neo4j, either it commits and all of the changes are visible and they're all visible at the same time, or it completely rolls back and none of it is visible to the outside world. So you can never end up in some sort of weird semi-committed state. The C is for consistency, which means that if you start in a consistent state and you perform a transaction and that commits or rolls back, you end up in another consistent state. The consistency guarantees that Neo4j gives you are that each relationship always connects two nodes. There's always a start node and an end node of a relationship. You can never end up in a situation where you have a relationship that goes to a node that doesn't exist. The I is for isolation, which means that a transaction doing changes, sure, within that transactional context, those changes are visible, but it's not visible to any other transactions. And for those of you further interested, Neo4j has a read committed isolation level as its default isolation level. And finally, the D is for durability. When a transaction is committed, Neo4j guarantees that it's written to disk. We guarantee that once your data is in there, it doesn't disappear. If the power should fail, the data, as long as you have seen that yes, the transaction was committed, the data is guaranteed to be there when the machine comes up again. Neo4j runs on all major platforms, Linux, Windows, Mac. This is a Mac. I'll show a demo here later on. So it obviously runs on this, and you have to trust me that it runs on Linux and Windows as well. It even runs on Solaris. We have one of our first installations still running on Solaris. You can run Neo4j in 2 modes. There's a standalone server that runs the Neo4j graph database to which you communicate through a REST API, or there's a embedded lean graph database kernel that you can use and embed into your application, kind of like you do with SQLite, yeah. I was thinking of Berkeley DB, but yeah, SQLite. So standalone is more like MySQL, and the embedded is more like SQLite. Finally, Neo4j is free software, free and open source, free as dictated by this deity. It's licensed under the GPL license with some advanced add-ons, such as high availability, licensed under the AGPL license. This pretty much means that you can use Neo4j for free in pretty much the same situations where you can use MySQL for free. So if you're writing a service and use the basic community edition of Neo4j, sure, go right ahead. You don't have to pay us a dime. If you need high availability for your service, you can choose to either open source your software and go right ahead, or if you don't want to do that, you can buy a commercial license from us. If you want to distribute software, you always either have to open source it or pay us the small amount of money that it costs. It's not that expensive. I think it's really cheap. We don't barely make any money on the community edition. Which brings us to, okay, I've completed the introduction about what a graph database is. I completed the part of the intro of Neo4j. Now on to why you should use a graph database. And this is my favorite all-time feature of graph databases. They're what we call whiteboard friendly. So remember I talked about, okay, when I implement an application, I start off by drawing something on a piece of paper or a whiteboard depicting what the entities are that I'm going to store and then how they relate to each other. So I would start by, okay, if I'm writing a competitor to Blogger, it's a blog hosting service. I would start with, okay, I'm going to have blogs, obviously. I'm going to publish articles on these blogs. And I'm going to have users. Okay, so I draw up my blog and my entries and my user, and I say that, okay, users are members of blogs, which means that they have publishing rights on that blog. We have articles that are published on a specific blog, and the articles are written by a specific user. Okay, and then I realized that, hey, Blogger has comments. I would need that too in order to be able to compete. So I add comments, and comments are comments to a specific entry, and they're also written by users. Okay, fairly straightforward. Everyone would start like this. You draw something to get an idea of what your model is. With a relational database, I would start translating this into a table. I would look at arities, and I would do all the work necessary to get to a normal form. With a graph database, I don't do that. I'm done. This is the model that I implement. So for the users, I have nodes representing the users. And then I have relationships to the blogs that they're members of. And I use member of as the type of these relationships. So I have a node representing me, and I have the blogs that I'm a member of. Then as I publish articles, I add nodes representing those entries. And I draw relationships to the node which blogs they're published on. And as comments are added, also, I add relationships denoting which user wrote them. In this case, I wrote all of these articles, which is actually a lie. I did write 2 of them, and one of them was written by someone else, and even though I've written 2 of them, I've only published one of those 2 that I've written. So I have relationships between these entities, and then as I add comments, I draw relationships from these comments to the articles to which they are comments to. Simple as that. The model I drew on the paper is the model I end up implementing in my application. But that's not the end of it. As my application evolved, I decided, hey, I'm pretty much just doing a clone of Blogger at this point. I want to add something more. I want to have an edge over Blogger. So I decided to introduce a social network. I add friends relationships between my users. In a relational database, I would have to rethink and redesign my schema and maybe stop the database to do schema to do data migration when I do my schema evolution. In a graph database, I would just start adding friends relationships. They're a new relationship type. It'll just work. And there's a bunch of other stuff that graph databases can do for you for free that comes with the database. And Andres will tell you more about that.
Let's see how this works. Hi, guys. Just a quick measure of the room. How many here are primarily Java developers? Just a hand up, right? How many here have downloaded and tested our software? A few persons. Thanks, Ian. Anyone used any other NoSQL databases out there? All right, cool. Have you tried to store graphs in a relational database? You have, right. And that's what I'm going to talk about. So if you're storing hierarchical data structures, there's a pretty good chance that a graph database is going to help you. So I also have a similar experience with, as you, Tobias, content management system that I built back in '97 that had a tree in it. And copying parts of the tree, we ran on SQL Server. Copying parts of the tree it took a day because everything had to be recursive and stuff. So this is a simple graph, and I'm just going to show you a couple of different ways that you could store that in a relational database. This is the naive implementation, probably the most common one. And it's awesome for writing. You can write it very quickly. It's not that good for reading because it forces you to either work with the recursive SQL statements that come up in some of the SQL databases, or to do a bunch of round trips. So horrible for reading, fast for writing. You have nested sets. Anyone used this? Thank you, my man. This is awesome for reading, but every time you have to insert a node in the middle, you have to switch everything, half of the database, one step to the right and one step to the left. So it's awesome for reading, not that good for writing. This one is, I've never used it myself. I've only seen it in books. Anyone here tried it? Oh. So the idea is that you write down in a string the path from the root of your tree down to every single node, which makes it possible to read quite fast. But it forces you to do string concatenation and weird stuff to read from it, and don't try to change the tree structure. And these are just trees of the data structures that are graphs. The trees are not elite at all. You could have directed acyclic diagrams, graphs like this, or just full-on graphs like the ones that we store in our database. So yes, you can store trees in a normal relational database. And yes, elephants can travel by bus, but it's not the best fit. So if you know that you're storing a structure that looks like a tree, and you're going to be querying on information that has to do with how the tree is built up, then a graph database is probably a good fit for your problem. But another thing that comes with knowing how your nodes are connected in a deeper level than a relational database knows allows our database to do some work for you that's not traditionally what you think databases do. So this is one of them. Every time you go to a LinkedIn page for someone that you are not already connected to, it shows you the path from you to that person. And to do that, you have to find the shortest path between two nodes in a graph set, right? I don't know how LinkedIn does it. They don't use Neo4j, unfortunately. But what you would have to do is you expand from the start, one of the two nodes, and you just step out to all the neighbors and continue expanding all the neighbors until we found the shortest route. This is something that Neo4j does for you. You just say, how am I connected between these? How are these two nodes connected through this type of relationship? So this is the exact query that LinkedIn uses. Is there a connection between these two that's no more than 4 hops away? And on a relational database, what happens is that we're storing all the 50 relations in a separate join table, right? So 1,000 persons means that that join table is going to have 50,000 items in it, and we have to traverse, we have to look through all those items. For us, when we're standing on a node, we don't care how many nodes there are in the database. We have a locality. So it's the only important number is how many relations do I have from that node to the next one, right? So for us, the speed limiting factor is how many relations people have, not how many people you have. Which means that if you grow, we're still the exact same speed. Doesn't matter for us. The only important part, how many relationships. The same is not true for other ways of storing relationships. The shortest path is one thing we can do. A-star routing is another thing that we can do. Sorry. So given a map, you want to get from the start to the goal, and you're not just interested in how many hops, but you're interested in something else, like, for example, the length of each segment or the average speed. I just want to travel through very fast roads. And that's something that we can do for you. You tell us which node you want to start from, which node you want to go to, and which property on the relationships between am I to take into consideration for the weight. So we can do that very, very fast. On a real use case, we've had 20 million nodes in that graph with 63 million relationships, and the average query took only 100 milliseconds. And the worst case scenario took 3 seconds, and that was a road that consisted of 5,500 segments. Try to do a self-join 5,500 times in a relational database.
And try to do it in under 3 seconds.
Yes. All right. Here you go.
Okay, so what we're showing you here is the Neo4j Graph Database server. It has a bunch of cool features, such as, where is my pointer? There. Such as looking at the database statistics, some detailed information, but what we're going to focus on today is the data browser. You can introspect the data stored in your database. The first view that you're presented with is this one, where you can where you see the properties on the node that you're looking at the moment. You can write in a search criterion here. You can choose to show the relationships. This is pretty simple, but what's really nice and fancy is the graphical view of this, where you can browse the data live. So what we're looking at here is a mind map representing this presentation stored in Neo4j. So we're talking about graph databases and how they can make you a superstar. And the main takeaway that we had from this was that you should use the right tool for each task that you're trying to solve. And we've shown you how which tasks a graph database does well. And we looked at the data model of a graph database, which is a graph. We looked at, Andres showed you some different kinds of graphs, such as the tree structure, which is the one he focused on. There's actually an even simpler graph, that is the list. A list is a very simple graph. Storing a list in a graph is just a linked list of nodes with relationships and connecting them. A tree is slightly more advanced than that. Let's see here. Okay. So a tree is more advanced than a list. And then we showed you that directed acyclical graphs are more advanced than a tree because they can have shared child nodes. And of course, a generic graph is even more advanced than a directed acyclical one because it allows to have cycles. We looked at how you query a graph in a graph database, and that you do this by traversal, such as the example we looked at for how do I know you, the LinkedIn example, or the friends of a friend's example, the first simple example that we looked at. We looked at another query model where you do algorithmic search, such as shortest path or A*, where we showed you an actual customer example that we had. Showed you the data model, that the graphs consist of nodes and relationships, that both nodes and relationships can have properties. Should have had mirrored. And of course, we showed you that graphs are whiteboard friendly, which was my favorite feature. We talked about Neo4j, which is our graph database. it said that it was open source software. You can use it, try it out, build a sample application and run it for a while internally in-house without having to pay us anything, because all your consumers are going to be your developers and they have access to the source code anyhow, so it's perfectly fine. We also said that Neo4j is a transactional with ACID transactions graph database. And we showed you a demo showing that, okay, this is what a graph looks like, stored in Neo4j, a graph database. And I think we have time to look at some code as well. So how do you work with a graph database? What does it look like when you interact? So we have this is our Java API. You get a reference to the graph database, and you can create nodes and set properties on the nodes. So here we create the first example that we had. We create the James node and the Mary node. We set the name and age on both of those, and then we create relationships between James and Mary, saying that James loves Mary, and we create a relationship from Mary to the Volvo, saying that this is the vehicle that she drives.
I see a bug in your code.
I know that you wrote the code.
35 shouldn't be a string.
It should not. 35 should not be a string. It should be a number. Right, it's called Morpheus here. You copy-paster. And as I said, Neo4j is transactional, so you would wrap this in a transaction. And we have a very simple transaction idiom that you use. So pretty much this is, so yes, it's Java. It's a bit verbose. It's a bit, there's a bit of procedure to it. But it's not that much. And I think this is the cleanest, in my humble opinion, this is the cleanest transaction idiom I've ever seen. You have a try finally, where you say, in the finally block, you say, finish the transaction. If the try block has reached the success invocation, the transaction will be marked as successful, and the finish method will commit the transaction. If some error occurred during this transaction block, and you never and you didn't reach the success invocation, the transaction will not have been marked as successful, and we will be regarded as unsuccessful and will roll back. And you can also explicitly mark the transaction for rollback by invoking a method called failure. But this is the basic idiom. And traversing, querying the graph. As I said, it returns paths. And you query it by defining a traversal description, looking at and telling it these are the what the relationship types are that you want to traverse. How deep you want to traverse. You say that, in this case, we say that we want to prune after depth 3. So we want to cut off our traversal after reaching the depth 3 in the graph. And then we tell it to traverse from the start node, me in this case, that we have gotten from an index. And for each path in this graph, this friends of a friend graph, we print the path from me to the relationship that we found. So this will actually, since we haven't defined which nodes to return, it will return all of them. So this will print the paths to my friends, their friends, and level 3, the friends of their friends. So friends of friends of friends. And our main takeaway, what we said is that you shouldn't ask how to fit your model, your data, into the database that you've been using for 30 some years. But you should ask which database fits my data the best, because your data is important. Do we have any questions? Yes.
I noticed you have relationship types, but not node types.
Yes.
But node types, so you just key value pairs. If in practice you end up having a lot of nodes of the same type, even
Yeah.
though it doesn't exist, doesn't that result in you storing massive amounts of redundant data?
Mm,
It's something that we've been talking about
Yeah.
a lot. If we should introduce node types.
node types are a slightly different thing than, or would be a slightly different thing than to what relationship types are today. So it's not types as in data types. It's more like labels. It's a navigational feature used for, okay, so I have a person, I want to find the either the friends of that person, then you traverse the friends relationships. So you look for relationships with the friends type or the friends label. Or you want to find the items that it owns, so that the person owns. So you look at the owns relationships. We don't do any enforcement of what kind of properties you can store with the relationships that has a particular type. The database does no such enforcement. So it really just is a navigational feature. It's just for, okay, I am at this type of node, and I go through a relationship with a certain type. Then my application knows that, okay, I know that I was at a person node, and I know that I traversed through a friends relationship. Therefore, I know that I must be at a person node. Yes?
So there's no enforcement if you want to sort of, like in the model, prevent James from marrying his Volvo?
No.
Okay.
That has to be done on the application level. But so what you do have today that is sort of what a node type would be is that you can have multiple indices. So you would store the person nodes in a person index, and you would store the car nodes in a car index. Yes?
The queries you've shown are exclusively based on the relationships, which makes sense in such a database.
Yeah.
But if you have queries which are more based on the key value, the properties,
Yeah.
as in who has a more expensive car than I have, or similar queries, to have anything supporting those kind of queries, or would that end up being, manual traversal, find nodes, compare values, and so on?
It would be an index lookup. So for that particular one, you would, who has a more expensive car than I have?
Yeah.
I would start at the node representing me, find out, list all of my cars. I might have several. So traverse to all of my cars, find the most expensive one, remember the price of that, then go to a car index and find and look and do an index lookup for cars that have a price higher than that price, and then from those nodes traverse to the owners of those cars.
What
Yes.
object type or what type do you get in the return from a query?
You get from a
Key value pair?
from a traversal query, you get a path or a set of paths from the start node to each of the nodes that have been found. From an index lookup, you get a set of nodes, which is really just a set of paths, because a path is the most simple path is a path of length 0 that has 0 relationships in it, which is just a node. So all the query results are always sets of paths. Yes.
Would you be able to join a transaction handed out by the application server?
Could you repeat that?
Yes, will you be able to join a transaction handed out by the application server?
Yes, actually, as of a few versions ago, we support joining an external transaction manager. There's still work going on making that more stable and solid. there are some glitches in the JTA specification, especially around how recovery is handled, which means that every single transaction manager does it slightly differently. But yes, we have support for that.
How about supporting two-phase commit?
Yes, we support two-phase commit. In fact, currently we have, we consider the index store and the graph store two different data sources, and many of our internal transactions end up being two-phase commits. We had a question behind you.
Yeah. How do you make the decision what to store as a key value on a node and what to store as another node in a relationship?
Very good.
So I could, for instance, say my car is worth 20,000 euro, or I could say it has is worth a relationship with a 20,000 euro node.
Yeah. So I would say that if the information is atomic, you should store it as a property, because duplicating such a property, such a small thing as a price, even if multiple cars have the same price, duplicating that information is actually going to be cheaper than creating a relationship to a price node. And also, it sort of makes sense from your domain model perspective. And that really is the most important part of it. You look at, okay, what kind of queries do I want to do across my data? If, for example, you had a data model where looking at the price ranges of a car, like what cars do I have in this price range, creating price range nodes is probably a really good idea. Yes.
So how close are you to solving the traveling salesman in a million times? The question is,
Yeah.
do you do stuff with this kind of
So, no, we don't do anything. We haven't proven that P is. We haven't done anything that proves that P is not that P is MP. All theories of computer science still hold.
But do you have heuristics in place for? Well, I mean, you need to use heuristics. For
Yes.
those kind of
So for TSP, we haven't done anything particularly geared towards TSP. As I said, we've worked on routing. It's one of the big things that we worked on, using A*, which is in fact a heuristic algorithm. And the main reason is that because we've seen interest from the geospatial community. We have a fairly ambitious project implementing what we call Neo4j Spatial, which is a spatial layer on top of Neo4j, supporting. Currently, it's at the level where you can store and efficiently query. What's it called? OpenStreetMap. And we're working towards making it fully compatible with OpenGIS or something. There's some tool suite that currently uses PostGIS, and we're working our way up to be a full-on replacement for PostGIS. We're pretty close, I think. Yes.
How the community, I understand it's there's Java support and REST interface.
Yeah.
But are there any love for like the .NET community, or should we just look at the REST interface?
We are. So currently, with the current releases, yes, that is the harsh truth. For .NET, you're left out in the cold restfulness. But we are.
There is a link driver that uses the REST interface.
Yeah.
So you don't have to write the REST.
No, exactly. And we are working our ways to making sweet love to .NET developers as well. Yes.
Do you give some comments on Spring's abstraction of your framework? When to use it or
Yeah,
use your stuff directly?
the Spring Data Graph abstraction. I think it's a really great thing. If we look back at this example, what you work with here is pretty primitive entities. Everything is a node, even though this is a person and this is a car. What Spring Data Graph gives you is an easy way to implement a domain model on top of Neo4j, kind of like what the Java Persistence API gives you for relational databases. And it's a very thin veneer, so it doesn't add much overhead to the graph. So you still get all the nice benefits of the graph database, even when working with this abstraction, and it really makes working with it easier. So if you're a Spring developer, I would very much urge you to use Spring Data Graph. If you want to use Neo4j, it's awesome.
It also makes it easier to do that kind of hybrid persistence.
Yes,
So
that is true.
Sometimes you persist, say, to MySQL and pass the object to the graph.
Yeah.
And again, very easy with Spring Data Graph.
Yeah, because it's just a different set of annotations to make it. This part is persisted in Neo4j. This part is persisted in a relational database using the APA. I believe you were first.
You're obviously very experienced with these kind of databases, and your main takeaway is that I should choose a database that suits my data. In your
Exactly.
experience, where are the dangers? Where is this not like, where are the limits of graph databases in general?
Do you want to take this?
Sure.
Mainly because I feel like I've been speaking.
No, it's the wrong way around, wasn't it?
You can hold it next to your face. Yes,
That is the wrong. All right. So I'm the former DBA, so I can relate to that question. I think it's graph databases have the strength of locality, so we don't have to look at the whole graph at the same time. We can focus on a very small piece of it, which makes us very fast. The relational databases have better support for going through a lot of very similar nodes, or similar rows at the same time. So if you're doing aggregations on a large number of rows, that's probably not going to be as fast on a graph database. That's the biggest sweet spot of sucking for us, is that one.
How easy would it be to do something like maximum flow or something? What kind of things with this?
That's your question, right?
Yeah, it actually is.
Is the
So-
algorithm guy.
Yeah, we have implementations for doing of such algorithms, for doing flow computation and for doing what else is there? There is flow, there is centrality.
Do you need to use one of your implementations, or could you
No,
do
you
something yourself?
you could do it yourself, just using the raw core API, just nodes and getting the relationships of nodes.
Okay.
But we do have a a library that is a set of algorithms that you can use. It currently, I think most of them are only exposed as a Java API with the embedded database. A few of them are exposed through REST, but not all of them. And of course, with things such as maximum flow, they are. Well, maximum flow is pretty simple because you have two connected nodes, so it does have locality. But we have things such as shortest path between all nodes using Dijkstra, and that is going to be limited by the size of your graph. It runs fine on small graphs up to like 1 million or so, but larger graphs than that, you're gonna start wishing you didn't have to solve that problem. What I wanted to say was about aggregation. That we were drawing this picture yesterday when preparing for this presentation. Let's say that you have a tree structure like this. And regardless of you can either store it in a relational database or you can store it in Neo4j. If you want to do something like aggregate from here and down on this level, aggregate values here, Neo4j is likely to be faster. But if you want to do aggregate over all of them here, a SQL database is going to be blow Neo4j out of the water. Not by complexity-wise, but by some factor at least.
Are there triggers? Because if you're doing some kind of aggregation, you could do some kind of logarithmic thing that keeps it calculated at all times. So,
sure.
So the graph actually would be much faster depending on how many inserts.
Yes, you could. Yeah, so you could trade read speed for write speed. So you could write some extra data into your graph as you update it. We've had customers doing this. One example was it was interesting. We had a customer modeling a file system where one common query they had was, what is the size of all files in this directory? And that turned out to be slightly too slow for them, doing this kind of aggregation, going through all of these and aggregating the sizes down here. So what they did was just, for the files, add the, if there was a file relationship, so they had file relationships and directory relationships. So for file relationships, they added they summed up the size of all of those file nodes and added that to the size of the directory. So they ended up, so when they did the actual, okay, what is the size of this directory? They only had to traverse directory relationships and summarize the size of the directories. And yes, to finalize the answer to this question, we do have a crude, rudimentary framework for building triggers. We have a transaction event system where you can listen to transactions when you can get an event when a transaction commits or rollbacks, and do further changes there. But we don't have a full-on system for building triggers such as PLSQL does, but we do have the foundations for building one. Yes.
I was just, you didn't mention in the REST API, is there a query language associated with Sparkle or something like that?
We do have support for Sparkle, but only through if you use our RDF abstraction layer. And for queries in the REST API, what we currently do is similar to similar to this. You send what you do is you send the definitions of what goes in here. So you would send a JSON object containing these are the relationship types I want to traverse and which direction you want to traverse them in. And you can also say I want to do this kind of pruning. And for the pruning and filtering of which nodes to include in the result set, what you do is you send in a text representation of a JavaScript function at the moment. It's not really the nicest way of doing things, which is why this guy he's the guy who's gotten furthest on this, but we're working on developing a nicer query language for doing the kinds of queries that we want to support on Neo4j. There are a number of graph query languages, but we think that most of them actually have the wrong focus. They try to be like Sparkle, only a fixed pattern and match this pattern, or they try to be a lot like SQL and deal with just select this data from a set of nodes. What we want to see in our query language is the ability to do the kind of cool stuff you can do with traversals today, arbitrary depth traversals, and of course the things that Sparkle does as well with pattern matching. So we're working on a query language. This guy has gotten the furthest. We currently have a in the office competition who can write the coolest query language, and this guy is in the lead. But I don't know when it will be production ready. But we're working on it, and there's something you can do today, but it will get better. Yes.
Do you support inferencing?
We have an external, so I'm guessing like type inferencing and stuff like that. So we have a library on top of Neo4j that we call the Neo4j meta model. I'm not really sure if it does the kind of inferencing you were thinking of, but what it does do is it adds enforcement of certain properties in the graph, like inferencing that, okay, this node has a relationship has one of these relationships. This means that the node is of type X. I'm going to assert that it has a certain set of properties. I think we're very much over time, and I would like to let you all get lunch. But if you have further questions, you can of course shoot us an email, or try to catch me afterwards. Once again, as you leave, if you want to write down our addresses or Twitter accounts, these are our details. Thank you.